Let's do an example. This is a three-part example for a mass on a spring. It says, a mass of 0.5 kilograms is attached to a spring of spring constant 2,000 newtons per meter. The mass is released from rest when the spring is stretched 5 centimeters. Find the frequency and period of the resulting oscillation. So luckily you'll find in this section that we do have a lot of easy plug and chug kind of questions, although we still always want to visualize everything. So we learned that the frequency for a mass on a spring was 1 over 2 pi times the square root of k over m. So all we have to do here is plug in our numbers. 1 over 2 pi, and use the pi key on your calculator. Don't just use 3.14 because that will be rounded too much. K is the spring constant right here, 2,000 newtons per meter. And then the mass is right here, 0.5 kilograms. So just plug all of this in the calculator and we'll get frequency of approximately 10 hertz. So 10 cycles per second. The period is going to be 1 over the frequency, so 1 over 10, so it's going to be 0.1 seconds. So this makes sense. If you have 10 cycles per second, then that means that one complete cycle only takes 0.1 of a second. I just want to visualize this before we move on to part B. It's good to visualize things. So let's say that we are going to model the motion of the spring with that cosine wave that we talked about. And let me just, we want to show 10 cycles here. So I have 1, 2, 3, 4, 5. I only showed five cycles here. I ran out of room, but just use your imagination. So what we're saying here is that we have 10 cycles per second. So if I only drew 5 seconds here, that means that those 5 seconds only take half of a second, 0.5 seconds. I'm graphing the time here on the x-axis and the position on the y-axis here. So 10 cycles would take 1 second, so 5 seconds take half a second. So can you see the period is a time for one complete cycle? Well, this must be 0.1, 0.2, 0.3, 0.4. So it's just good to visualize and see, okay, well, one cycle, that's the period, is 0.1 second. So you can see that inverse relation between frequency and period. Let's take a look at part B. This says find the equation for the position of the mass as a function of time. So we said that a mass on a spring is the position is going to be described by this cosine function. X as a function of time equals a cosine of 2 pi f t. So now we're seeing how do we use this equation. Well, we need to figure out what the amplitude is. And it says that the mass is released from rest when the spring is stretched 5 centimeters. So if we go back to our picture here, this is when we started the motion, when the mass was over here. So that means that this distance from here to this equilibrium position is 5 centimeters. 5 centimeters can also be written as 0.05 meters. So that means that the amplitude is 0.05 meters. And then we just have to plug in cosine times 2 pi, and then the frequency that we just found in part A was 10 hertz. And the time, we can leave it there because we're looking for the position as a function of time. And I usually don't bother putting the meters in here because I feel that putting the units in this equation just makes it look confusing, because maybe you'll think that m stands for mass. So let's just not put the unit in here and just write 0.05 cosine of 2 pi times 10 times t. So we can simplify that. It's 0.05 times cosine of 20 pi times t. So this is the equation of motion for this mass on a spring. This equation describes this function that we drew here. If you can plot this cosine function in your calculator, it should look just like this. So this question is not asking us for a number, it's asking us for this position as a function of time. So it means that now, if you plug in any time that you want in here, you can figure out the exact position of the mass. And that's what we're doing in part C. It says, what's the position of the mass at a time of 0.25 seconds after it is released? So we just came up with the equation x as a function of t. Now it wants us to plug in 0.25 seconds for t. So when I put it here, I'm not saying that I'm multiplying x by 0.25. I'm just saying that I'm finding x when time is equal to 0.25 seconds. So it's going to be 0.05 cosine of 20 pi times t, where t is 0.25 seconds. So you plug all of this in your calculator, and you're going to get x is equal to approximately negative 0.05 meters. Now, I strongly encourage you to put this in your calculator, because chances are, if you put it in your calculator right now, that you're actually not going to get this answer. And this is because your calculator must be in radian mode for this section on simple harmonic motion. Make sure that it's in radian mode. And this is because this unit that we have inside the parentheses, inside the argument for the cosine function, it was 2 pi f times time. And there's no degrees here. It turns out that 2 pi f is a number of cycles per second, but because you multiply it by 2 pi, it actually becomes radians per second. And so then you multiply that by seconds, and you get just radians. So make sure that your calculator is in radian mode. Now, one last thing is that you didn't even have to plug all of these numbers in to figure out the answer to this question. If you drew the picture, what is the position after 0.25 seconds? Let's go back and look at our graph. We have 0.1 seconds, 0.2, 0.3. Can you see that 0.25 seconds is right here? In between the two peaks? It's right here. Where is the mass after 0.25 seconds? It's right here. And this is the peak, but in the negative direction. So instead of being 5 centimeters up, it's 5 centimeters down. So it's negative 5 centimeters. And how do we write negative 5 centimeters in meters? We write negative 0.05 meters. So I always like to visualize the motion just to help make sense of it and all of these new variables. We'll talk more about simple harmonic motion in the next video.